Okay, I really like this standing wave problem, just because I feel like it's really thorough and straightforward, but it allows you to explore different aspects of the standing wave. So let's see what we have here. We're given some string. The mass of the string is given, the length and fundamental frequency. We're also told that the string itself is not resonating at its fundamental. It's resonating in its third mode. Okay, so I want to try to capture that information, just that even like that top sentence right in the problem statement, and capture it in pictures and get everything I can out of that statement in pictures. So what we're given is a string, and we're told something about its fundamental mode. So fundamental mode is super useful. I've mentioned this before, but don't just skate over the fundamental mode of the string. You care about that. So I'm going to start. It's easy to get distracted by like knowing that it's in its third mode, but I'm actually just going to start by pausing and looking at the fundamental mode here. Now, what do I know? I know the string has some length 2L. Really important that I draw that out too. And then I'm also going to label on here, just as a reminder for me and for you, that this is 1/2 of the fundamental wavelength, right? That's 1/2 of a wavelength. I can see that on inspection just by looking at it. We're told that the fundamental wavelength is equal to big F in this problem. That's one of our givens. I can look at the situation and I can see by inspection that the fundamental wavelength is equal to 4L, because it's going to be equal to 2 times the length of the string. And that what that allows me to do right here, just looking at the fundamental, if I wanted to, is I could solve for, I have the frequency, I have the wavelength. So think about it. What does that make you realize you can solve for? You can solve for the wave speed. So right away, just by using this information here, given about the fundamental mode, I can actually solve for the wave speed on this string. And that wave speed is, I can set that equal to the fundamental wavelength times the fundamental frequency. So that's going to be equal to 4LF. That's useful. I've got the wave speed. So you kind of like analyze the heck out of the fundamental, make sure you're applying everything in the problem statement to that before you move on and look at the other modes. There's a reason it's called the fundamental frequency, and that is that it really is a signature of the system and sets up, you can extract behavior of the rest of the system if you know the fundamental. Okay, so that's done. Now let's go to what we're told, how it's resonating. The string is not, we're told this information about the fundamental, but that in the instance of this problem, the string is actually resonating in its third mode. So I'm going to go ahead and draw that out. So it's in its third mode, which is the n=3 mode, right? Strings are so nice and straightforward when it comes to standing waves. The string length hasn't changed. It's still 2L. And here, I really encourage you to say like, oh, look, here, for instance, is one wavelength, right? Going to capturing 2 loops, you could say, of the wave. I know I didn't draw it perfectly, but here's basically one wavelength. So this is what I could call lambda sub 3. So it's basically 2/3 of that 2L, right? So this first question is about this. This first question, A, what is the frequency of the wave on the string? Well, I can, by drawing this out, by looking at it, and I can deduce the wavelength, right? The wavelength is going to be equal to, of the third mode, 2/3 of the string length, which is equal to 2L. And that gives me 4/3 L. Okay. And you might be saying, they're not asking us for the wavelength. Well, yes, I know, but I want to try to solve for the frequency. So I understand that you can just say like, well, I have memorized that everyone's a multiple, so the n=3 is just 3 times the fundamental, and that's fine, but I want to show you, basically that could be your check to this other way of solving for it. So we also know that wave speed is equal to the product of the third mode wavelength times the third mode frequency, right? So I could leverage that and say the third mode frequency is equal to wave speed divided by wavelength for the third mode. And if I do that, my wave speed, I've already solved for that in the fundamental case for LF. I divide that by my third mode wavelength, which is 4/3 L, and what I'll get will be no surprise, and that's 3F. But I still wanted to take you through this exercise because it's good practice for working with these equations. These are small equations, but you really have to use them in the right way. So there's our part A. Part B asks us, what is the speed of the wave on the string? Well, actually, I solved for that already up here when I was analyzing the fundamental. So we can then move on to, so here, this is my answer for part B. We can move on to part C. Part C asks us, what is the tension in the string? So again, we have to go to this all-important equation for waves on strings that relates the wave speed, the tension, and the linear density. So the tension is going to be equal to the product of the linear density and the square of the wave speed. So the linear density actually was given in this problem. If you go back and look at the problem statement, you're given the mass and length of the string, aren't you? So if we know the mass and length of the string, then the linear density is just going to be m over 2L. We've got it. So we know the linear density, we know the wave speed, we can solve for the tension here. So linear density, which is m over 2L, and multiply that by the wave speed squared, 4LF squared, and that's going to give me 8F squared ML. Okay, now part D. So that's the tension, just to be clear, tension in the string. Part D for this problem asks for what is the wavelength of the sound wave created? So like, whoa, slow down for a second. Wavelength of the sound wave created. So now this is a sound wave in air. So don't confuse that with a wave on the string. When you're hearing like a guitar or violin string, you're not actually, it's not the wave on the string that is causing a pressure differential in your ear for you to hear it. It's actually the sound wave, right? So the wave on the string, what it does is it mechanically vibrates, as you know, and that causes a vibration in the fluid, which is the air. Remember that sound waves need a medium. So the air is then put into oscillation. That's what makes it to your ear, and that's what allows you to hear a sound from the wave on the string. So cool. So we just want to remember that we're thinking about the sound wave here. So for the sound wave, I'm given the speed of sound in air, which is given to me as c. And again, I can use the equation that relates wave speed, wavelength, and frequency here. So this is going to be the wavelength of the sound wave. I'm going to subscript that with an S for sound. And remember that the string is vibrating in its third mode, so that'll be F sub 3. And I want to solve for the wavelength of the sound wave. That'll be equal to the speed of sound divided by the frequency of the string. So that's just going to be simply C over 3F. And this should remind us that when it comes to frequency, the frequency of a wave depends on the source. So what the wave on the string and the wave in air have in common, the only thing they have in common is the frequency. And that's sort of cause and effect situation, right? The string is vibrating at a particular frequency. So just imagine it in your mind going back and forth at a particular frequency. That vibration is what forces physically the air molecules around it, around the string, to start vibrating, right? The string is not vibrating in a vacuum, it's vibrating in a fluid. So it's going to be disturbing that fluid when it vibrates at the same frequency. So the frequencies are the same. Because the wave speed of the sound wave is different, the wavelength is different too. So remember that I've said this before in here, but frequency depends on the source, wave speed depends on the medium, and wavelength adjusts. That's true here as well.